Hey, friends! Thanks for tuning in. I wanted to let you know that in the video description below, we've got something pretty cool for you. We've put together a free exam that covers some basic knowledge about chiller systems, and it even comes with some extra information to help you out. So, make sure to check it out. Best of all, it won't cost you a thing. That's right, it's completely free.
In this video, prepared by Confort Empresaria Latin America, we are going to quickly perform the calculation of the system that we are showing on the screen. To explain the technical concepts that must be mastered, we have divided this content into 15 very short notes, which have the essential terms that the technician must master. Once the respective explanations have been developed, we are going to apply everything we have learned, developing the calculation of the system.
Be with us and subscribe to the channel.
Let's go with note number 1.
Note 1. The anemometer is the essential device to measure speeds and inducted airflows.
Note 2. A proper flow rate of air to be supplied to a room is 400 cubic feet per minute, CFM, or 680 cubic meters per hour, multiplied by each ton of room cooling.
Note 3.
The most commonly used air velocity inside ducts is 10 meters per second, or 2,000 feet per minute.
Note 4. Pressure values within duct systems are small magnitudes, which is why special units are used for their measurement, such as inches or millimeters of water column.
We stay in note 5. The equivalence between pressure units used in pipelines and traditional pressure units are exaggerated. For example, 1 millimeter of water column, a unit for ducts, is equal to 0.1 kilopascal, or 0.145 psi.
Note 6.
The air, when passing through the ducts, suffers a loss of pressure due to friction. These losses in some cases are close to 0.1 millimeters of water column for each meter. Note 7.
If, for example, for an 8-meter duct, the pressure loss due to friction is calculated by multiplying the 0.1 millimeters of friction by the 8-meter duct.
Thus we have a loss of 0.8 millimeters of water column. We stay in note 8. The duct system fan delivers two types of pressure, dynamic and static pressure. Note 9. The sum of both pressures represents the total energy that the fan delivers to the air. Note 10. The static pressure, for example, measured in millimeters of water column, is the pressure necessary to overcome the friction of the air with the walls of the duct, and it must be supplied by the fan in order to get the air to all the grills. Note 11. The dynamic pressure has to do with the speed that the air carries inside the system, and also depends on the flow rate and the area of the ducts. Now we are going to classify the air conditioning ducts by their speed. To do this, we will take into account three basic categories. Low-velocity ducted air conditioning systems. These systems are characterized by larger duct cross-sectional areas, resulting in air velocities of up to 2,000 feet per minute. These distributions are used in most air conditioning installations because it is quieter, has less friction losses, less fan power and less air leakage. On the other hand, when we talk about ducted air conditioning systems with medium speed, we refer to installations which are characterized by air speeds in the range of 2,000 to 2,500 feet per minute. Now we have high-velocity ducted air conditioning systems. These systems are characterized by smaller duct cross-sectional areas, thus air velocities greater than 2,500 feet per minute. High design speeds result in lower initial costs for the duct manufacturer, but require increased fan effort to get air to all points. That is, higher operating cost for the user. Let us now study the airflow term. The flow rate is the amount of air in volume form that passes through a duct. The most widely used units to measure the airflow of an installation are cubic feet per minute, FM, and cubic meters per hour. As the density of the air changes very little in duct systems, we can say that it is true that the volumetric flow of air entering the fan of an installation is equal to the sum of the volumetric air flows at the outlets of the grids. One way to relate the flow and the speed of the air is with the formula that says that the area of a duct is equal to the division between the flow of air between the speed of the same. In general, we can say that for every ton of cooling that the air conditioning system handles, the fan must supply an airflow of 400 cubic feet per minute. Now we are going to classify the air conditioning ducts by their pressure. Low pressure air lines. These are systems with pressures less than 3 inches of water column. In general, in these systems, the air velocities inside the ducts are less than 1,500 feet per minute. Medium pressure air ducts. These are systems with static pressures between 3 to 6 inches of water column. In general, Duct velocities are less than or equal to 2,500 feet per minute. High-pressure air ducts. These are systems with pressures between 6 to 10 inches of water column. Static pressure is generally limited to a maximum of 7 inches of water column, and duct velocities are limited to 4,000 feet per minute. Systems that require pressures greater than 7 inches of water column are normally unwarranted and could result in very high operating costs. In this last note, we are going to show a basic calculation for the design of an air conditioning duct installation. On the screen we can see a diagram. It is a short installation. In other words, the distance between the fan and the last grill is close to 8 meters or 25 feet. As the system is short, it can be considered that the original fan of the system has enough pressure to get the cold air to all the grills. This means that we are not going to worry about the pressure of the installation, but only about the speed.
Another important fact is that the total supply flow is 1000 CFM, divided into 2 outlets.
As we studied in the previous notes, 400 CFM is required for each refrigeration ton. So we are talking about 1.25 refrigeration tons for each outlet.
That is to say 15,000 weather per hour.
To perform the calculation, we are only going to divide the flow by the design speed.
If we take a silent speed of 1500 feet per minute, 7.5 meters per second, we have
to calculate the area of the duct. First work with the flow that handles 1000 CFM, and this is divided by the design speed, that is 1500 feet per minute. This division results in 0.66 square feet. If the duct to be installed is square, we must only take the square root of the area of the square. In this way we obtain the value of each side. The root of 0.66 square feet is 0.81 feet. In this way the square has dimensions 0.81 feet by 0.81 feet.
We can notice how the installation has a return duct. This return handles 900 CFM. This means that of the 1000 CFM of cold air that enters the premises, 100 are sent to the street, and 900 CFM return to the machine, to be cooled again.
Thus, 100 CFM of new air must be introduced, to carry out the renewal, and recover the 100 that were discarded. The renovation is carried out to maintain the environment of the premises, with a low concentration of pollutants. Thanks for joining us.